Welcome everybody. We are gonna wait for everyone to join in. It's gonna take a few seconds for attendees to join, so please bear with us while we wait for everyone to join this webinar. I'll start by introducing myself. My name is Alessandro. I'm a professor at the University of Birmingham, and I'm part of a team of people who build and work on something we call Discover Materials. Discover Materials is a partnership between UK universities that teach material science and engineering, the Henry Royce Institute, and we are promoting material science as a discipline and showcasing the wonderful career opportunities that happen from doing a material science and engineering degree. So we've had a week of videos and activities for you. Hopefully you've enjoyed what we have done so far. And for today's event, we have about 160 people registered from all places around the world. So thank you very much for joining us and welcome to this webinar. So if you would like to see what we've been up to for the past week, if this is your first time to join us, please visit our website, which is www.discovermaterials.uk. And we are recording today's session. So if you happen to miss any of this, you'll be able to catch up on the recording, which we'll be sending to you via email. We'll send you a link to you via email. So this is a webinar, so your camera and microphone have been switched off, and there is no worries about appearing on screen. It's only us who appear on screen. So if you drop out of the internet sessions, of the webinar sessions for internet reasons, just rejoin and you'll be able to catch up on anything you've missed. The way that you interact with us is through the Q&A box. So at the bottom of the webinar, you'll see a Q&A box, and you should be able to use that Q&A box to ask us any questions throughout the session. And there will be people on hand to answer even as Marty is covering his wonderful session. So please go away and ask questions if you have any, and we'll be able to answer them live. And then we'll gather any questions that we would like Marty to answer towards the end of the session and ask Marty directly. So today we have a live material science show by Marty Jopson. Marty is a regular on the BBC's The One Show, and he will help us discover a little bit more about materials in your mobile phone. Mobile phone has been very important during lockdown. I'm sure you agree. And so it's good to explore some of the material science at the bottom of a mobile phone. We will then, at the end of the session with Marty, we will launch a new video to showcase the field of material science and engineering. And then at 2:30 p.m. British time, we will have a live Q&A with some academics and recent graduates from material science and engineering departments and employers in the field. And we will also announce the prizes of the best infographics from the ones that we have received. So with that, I think I can now hand over to Marty. And so I'll make him spotlighted. Just give me a second. Here we go. So Marty, you're now spotlighted and you should be able to.
Excellent. Thank you very much, Alessandro. So my name is Marty Jopson. Hello, everybody. Welcome to my my kitchen table and welcome to my kitchen. I'm here to talk to you today about material science, and specifically the material science inside this beastie here. This mobile phone is the subject of my, because let's face it, we've all been spending all our time online, and I thought, what better place to start looking at some interesting material science than in this? And the more you dig in, the more you find. Now, I have got the Q&A box open, so if you post questions, I will try and answer them if and as they come in. I'll sort of try and incorporate them. If I don't, we'll leave them to the end if I skip over them or something like that. So anyway, let's start out with this thing. Let's start out. I'm going to ask, we're going to try and do some polling as well. Let's try and see if anybody's actually listening, see if anybody's actually out there, more importantly. We've got a few polls, and I believe either Alessandro or Erin is going to be actually running these, depending on who's got their finger on the button. Let's start with the first question on the poll. The first question I had on this was, do you own a smartphone? I'm not going to give you very long to answer this because it is ridiculously simple. Oh, I can't vote, apparently. It came up. I was trying to vote for it. I'm just going to give you a few seconds. So if you're this, let me know. Do you own a smartphone? By which I mean one of these things, not one of those bricks, not a Nokia brick. Right, I think we've had enough of that. Let's show us the results on that, if we've got any results. There you go. Everybody owns a smartphone. No great surprises. Let's go straight to the second question. What brand of smartphone do you own? The reason I say is no great surprise on if you own a smartphone, because when I looked up the statistics on this, they reckoned that 100% of teenagers, and that's the sort of people I'm expecting to be watching, have a smartphone. 100% of them in this country. I mean, clearly there are some people who don't, but for the population they sampled, it was 100%. So the second question, do we have the brand? Yes, there's the brand. Apparently there are other brands. That's quite interesting. 38% of you saying there are other brands. That's slightly surprising, because in the data I found, the top, let me just double check, the top 29 phones, the most popular, now question mark what popular is, were either Apple or Samsung. Started out with the iPhone 8, the Galaxy S7, then the Galaxy S8, then the iPhone 8 Plus, and then it carries on Apple Galaxy, Samsung, and it's only when you get to 30 do you get a Google, 31 is a Nokia, and you don't see Huawei until 38. Okay, so what about the next, one of the critical questions, how long do you use your phone each day? So just tick the one that applies to you. And by this, I mean sort of, how long do you spend using it? Because we do use our phones an inordinately large amount of time. Let's see, we've probably had enough of that. Let's go to the answers for that. So I probably use there you go. That's pretty much what I'd expect to see. We're a bit low on the very high end users there, because the last data I found on this, which admittedly was a few years old, was that 20% of teenagers say they use their phone for 7 hours or more a day. That's a lot of time spent peering at your phone. I mean, it's a question as to what constitutes using your phone. I mean, if you put it down to scratch your ear or something, are you still using it? But anyway, right, good. That's got you answering questions. So if you've got any more questions, stick them in the Q&A and I'll see if I can answer them. Right, let's get straight into it. So, okay, here's my phone. What's it made of? What's actually inside a phone? That's what I wanted to find out. So again, I went back to, actually it was from some people from Sheffield Hallam University that I approached to help me with this. And I wanted to know let's start with what elements are in your phone. What of the elements in the periodic table? So here's a full periodic table for you in all its beauty. And I'm now up in the top, but here's all the elements. I'm going to compact it so that we can see a bit more. You can actually read what's on the screen. So obviously these elements down here, these are all the transition elements. They are tucked in here normally in the full table, but I've sort of put them down at the bottom. So in a phone, you've got all of these elements pretty much. Now there might be a few more, and there probably not all phones have everything. There are some more obvious ones that you've got in here. So things like iron there. Number 26, 26 iron, cobalt, nickel, fairly obvious things that you'd expect to be in there. It must be said, I haven't got copper listed, and I know for a fact there is copper, so that's at least one that's wrong. I've just spotted an error in my own table. But then you've got aluminium, things like that. And then there's a few other weird things. There's hydrogen, obviously, because there's some organic compounds. You've got chlorine and bromine, potassium over here, and elements over here, potassium and magnesium. But then you've got a whole ream of really weird elements down here, like praseodymium, europium, gadolinium, terbium, dysprosium. You have to look, I can't pronounce these things, dysprosium. But also you've got some of the rare earths as well, things like silver, gold, platinum and palladium. So you've got actually a huge number. If you count up what's in there, there's at least 38 different elements in your phone. Compare that to, well, yourself. There's relatively few elements in a human being. There's only about 24 elements in a human being. Now, obviously, if you ground up a mobile phone, if I took a bite of this, then I'd have a whole load of more elements. But I mean normal elements that are in your phone, things that are normally found inside your body that make up the bits of your body. So relatively speaking, the phone is much, much more complicated. Right, let me go back to the main thing there. I'll turn that off. That's good. Right, there you go. So I've got loads of cameras and things all here that I have to control, and all of it actually is controlled through my mobile phone. I've actually got my there's a little control panel there that allows me to turn everything on and off when I need it. So that brings me to the screen, because obviously without a screen, the mobile phone, well, I mean, it's a phone, and we can talk about that in a bit, but the actual screen itself is pretty vital for a smartphone. It's the screen that makes it into a smart phone. If it wasn't a screened phone, then it would just be a Nokia brick with buttons. So the question is, how does the screen work? What's going on with the screen? If you look at the screen under a microscope, and these are my two beautiful microscopes. I'm given the microscopes by the folk at Zeiss, over there. The folk at Zeiss who make microscopes, they give me these and they say, go away, talk to people, show people things under a microscope. So I do. So let's stick this underneath the microscope, just like that, and see what it looks like. Oh, hang on a minute. I need to use this to turn on the microscopes. There we go. So I shall put that under the microscope, and we'll start sort of down here like that. And then if I focus, and that's what the screen of your mobile phone looks like. Now, this is at relatively low magnification. I've got ×10 here and ×10 up here. So we're about 100 times magnification. And suddenly you see that the screen, and this bit of the screen that we're looking at is a white bit. So this is a white bit of the screen. It's made up of all these tiny, tiny little pixels. And this is one of these super high resolution screens that the Apple stick on. And if I move the phone just a bit, you can see if I go, where am I going? Until I get into the red section. Here's the red section, again, focus. You can see this bit here is the red, and it's, I'll just hold it up to you. It's that bit there. You can't see that, never mind. There we go, the camera on the phone. This camera up here takes a little while to get itself sorted out, and it's decided that that's a little bit more orange than it is red. But if I go back over to the white, there we go, that looks better. So it's white balancing itself. And then we go into the red, and there's the red. I can show you a blue. Here's the blue. Here's a nice pure blue. And you can see when if it's out of focus, it does look blue, and that's what your eyes are seeing because they can't pick up the individual pixels. But then we zoom into it, and there is the blue. Although you'll notice that this blue does in fact have a little bit of green in it. There's a little bit of green going on in there as well. And then, talking of green, let's go to the green. There's a green. That's some sort of letter. I don't know what that is. An O maybe, or something like that. And obviously this bit here is white. And down here, we've got just the pure green going on with a little bit of blue in there and a little bit of red in there. So you've got these individual pixels. The pixels are essentially, I like to think of them as little shutters, because what you have inside your phone is behind the back of the phone screen, there is a constant light source, a completely flat, smooth, even white light source that is shining up through the screen at all times. Certainly, unless you've got an OLED phone. Well, let's not go into, oh, actually, that's somebody's just sent me a message on my phone and it's just popped up. You see, there it is. So my phone keeps changing. So unless you've got an OLED phone, in which case things get more complicated, but if you've got one of these, which is a liquid crystal phone, essentially what you have is little shutters over the top of this white background, this light that's shining through, and the shutters can be closed or they can be open. And when they're open, obviously the light goes through, and if it goes through, it then hits a little patch of coloured material, and that colours the white light. And there are different colours for different patches for different things. So obviously over here, all of these patches have green over the top of them. And all of these patches, you know, there's a red bit and there's a blue bit, and you've got the different colours that make it up. And that's how we make it up. And these things are absolutely tiny. Right, let me go back to, if I pull that out and go back to this, then I can come back here. Oh, that's better. And in fact, where am I? If I click on that, many of the colours that you get on your phone come from some of these crazy ones down here, some of these really rare earth elements down here. A lot of those are the ones that give you the colors on your phone. But how do we actually get the shuttering effect? Because this screen here is clearly made up of absolutely millions upon millions upon millions of individual shutters. Every single one of those tiny little pixels is a shutter that can be closed and opened automatically by electricity. How does that work? Well, to understand that, we need to take a step back and we need to talk about polarization of light. So, okay, light, and this is where I wish I had slightly more room. Light is a wave, okay, we're happy with that. It's a particle as well, but let's talk about it as a wave. And the light that comes down from, say, the light bulb that's above me here, that's coming at me here, doesn't come at me just like this, or like this, but it comes at me in all different angles of wave, okay? And it is not what is called not polarized or unpolarized light. So you've got all these different angles of light coming down at you. Polarization just removes most of the angles and leaves one angle left. So if, for example, this light is coming at you like this, polarized light might be, for example, just the up and down parts of the light, and the rest of the light doesn't get through. The way it works, it's very simple. A polarization filter is kind of a bit like one of these. It's a bit like a sort of a griddle. And if the light lines up with the slots in the polarization filter, it goes through like that. And if it doesn't, then it can't get through. So all of this light is blocked, but this light goes through. So you only get the light that's going up and down vertically goes through my filter. I'm going to put these down here. Now, these are sheets of polarizing material. They're just cheap sheets. And what they've essentially got is they've got lots and lots of molecules in them. They stretch the plastic as it's made so that all the molecules are lined up vertically. And that means that when that light comes along, only the light that's going up and down goes through the sheet. And as you can see, it cuts out quite a lot of the light, but not all of it. Now, here's a second sheet of polarizing material, two completely identical sheets of polarizing material, both polarizing up and down. If I cross them over, you can still see through just about. Can you see me? Yeah. But if I turn it over, it goes completely black. Turn it back, and it's see-through. Black, not see-through. Black, not see-through. Turn that one, it goes black. And that bit, you really can't see through at all. If I hold it further closer to the camera like that, I'm getting a lot of reflections. Try and get rid of those. But where it's overlapped like that, and then I turn it like that. And the reason is now because I've got two different sheets of polarizing direction. So the first sheet is polarizing the light like this, and the second sheet is polarizing it like that. And since the first sheet only allows light that's going vertically through, and the second sheet only allows light that's going horizontally through, you see nothing. Now, this is absolutely crucial for the way your phone works, or at least the way your screen and any liquid crystal screen works. And this is where it comes to the crystal part of it. And I'm going to show you some crystals underneath the microscope using what's called polarization microscopy, which essentially is that I just used two sheets of polarizing material above and below the sample. So what I have here, this phone's all getting in a tizzle. Let me show you this. What I have here is a glass slide which has a little bit of sucrose that I melted in water and then dissolved in water technically, and then just dropped onto it and allowed to dry, and it's formed lots of crystals. Can you see that? And if I put that underneath this microscope here, swap microscopes, that's what it looks like. A kind of a splat of crystalline goo. And at the moment, I'm just shining light on it from the top. But if I shine polarized light through it, something weird happens. And to show you that, what I'm going to do is I'm going to point my desk camera at my microscope and show you what I'm doing. I'm going to take out the little background disc here, and I have here a polarizing filter. So it's a see-through filter, okay, that polarizes in the direction of that white line there. And I'm going to pop that in there like that. And then I've also got a polarizing filter immediately above this, here, just above here, at the bottom of all the lenses up here. And what I can do is I can arrange for the two polarizing filters to be at right angles to each other. I'm going to shine some light through it. Turn the top light off. Right. Let's just have a look. Right, that's good. Let's go to the microscope. So what you have here under this microscope, okay, there's my fingers, is two polarizing filters that are lined up so the light passes through them. If I now turn the bottom polarizing filter until it's at right angles to the top polarizing filter, no light gets through. So it's exactly the same as when I had the two polarizing filters and I turned one through 90 degrees to the other like that. If I now put the crystals under that, something rather magical happens. You start to see them because you know that it's completely black, no light gets through, but you put the crystals under, and where the crystals are, the light goes through and you get these beautiful colored patches. Look at all this lovely color that's coming through. And that's because if you've got a crystalline substance and you put polarized light through it, it twists as it goes through. And if it's just the right thickness, it will twist by 90 degrees, it will go through, and then it will go through the second polarizing filter. So the light comes up polarized, say this way, it goes through the crystals, is twisted 90 degrees, and then goes through the second one. I'm going to switch to this microscope now because I actually have, this one allows me to show you the detail and allows me to show you much nicer detail. So I'm going to pop this under here and find my specimen, which involves me zooming right in on it because we were zoomed right out. Let's find a good spot. And for this one, the microscopy on this one, that's a nice patch just there. And then I'll swap microscopes. There we go. And there, look at that, isn't that beautiful? Fantastic colors you get from cross-polar microscopy. So this is sucrose, which is sort of everyday. I've got another one here. This one is citric acid, same sort of thing. I'll pop that one under. Let's have a look at what that one looks like. Let's stick that one under. And this one, you get this sort of crazy sort of lunar landscapes. You can see the individual crystals there, and the microscope camera is just adjusting itself. Some beautiful, beautiful colors. Look at that, isn't that fantastic? There. And so depending on the different crystals, the reasons why you get colors is because different thicknesses, different crystals will cause different light, different wavelengths of light to bend and twist more or better so that it goes through and you get the different colors showing up. But my favorite though is this one. I want to show you this one. This one is aspirin. You take aspirin, you dissolve it in ethanol. It dissolves very well in ethanol. And then you put it on a slide and allow it to evaporate. And what you end up with is a completely different type of crystal, which is not in focus. Let's get it in focus. You end up with these sort of amazing little crystals that start at a point, the point here starts in the middle here, and then it expands out. And as it expands out, it creates these sort of, I don't know, sort of Maltese cross patterns. And then when they meet another crystal that's growing, you get these interfaces here like this. And if I find a good patch, oh look, there's an interesting patch where it just hasn't done that at all. It's done something completely different. And there's one that looks like, again, it looks like some sort of beach or something. And these are very microscopic crystals. But look at that. Whoa, isn't that amazing? The colors you get, the beautiful colors. Oh, it's become less colorful for some reason. It's got its auto white balance on and it kind of calms down the colors every now and then. But you get these fantastic crystals forming. I'm just looking, there's some other good patches in here, I know. Here's a patch with lots of really tiny little crystals forming. And I can actually spend hours just hunting around and taking pictures of the best crystals. Look at that, isn't that beautiful? And all of this is caused by crystals causing the light to twist because I have a polarized filter here at the bottom and a polarized filter here at the top. So just like these two polarized filters, and they're at right angles to each other, no light should go through up here underneath. You should get no light coming through, but you do because the crystals cause it to twist. Let's pull this out. Oh, look, there's a question that's popped up there. Is the aspirin methanol dissolved showing semi-crystalline features? No, it's showing completely crystalline features. I'll talk about semi-crystalline features in a minute. And it's actually not dissolved in methanol, it's dissolved in ethanol. I'm not sure what its methanol solubility is, but quite frankly, methanol's horrible. You don't want to fiddle around with that. Let me show you, though. Let's go on to something that is semi-crystalline. Good question. And let's talk about how your phone works. Because, okay, so I've said that this is what's going on. Your phone is a liquid crystal display, but I haven't really explained how that works. Well, what you have on your phone is a polarizing sheet on top and a polarizing sheet underneath all the electrical bits. And then underneath that is the light source, which shines through the whole thing. And these are cross-polarized sheets. So one is like this and one is like this. So no light should go through at all. And the reason light goes through is because between those two sheets is what's known as a liquid crystal. Here's a liquid crystal. Obviously, this is a molecule of liquid crystal. And this is a standard sort of molecules building system. So black is carbon, white is hydrogen. This one is part of a mixture called C7. This one here, which is a common sort of variety that people use in research. This one is, this is oxygen. Obviously, there's an oxygen there, but that's not really important. This one, though, is important. This is a nitrogen at the top, and it is highly charged. Remember that bit. I'll come to that in a second. But the thing about the liquid crystal is if you look at the structure, it's got two benzene rings there, one there and one there. And these are quite rigid, and they create a rigid structure at the top here, okay? That ain't doing anything really. At the bottom, you've got a long wiggly tail. And that's why this is called a liquid crystal, because these bits form a regular crystal lattice if you allow them to. If you just leave it as a liquid, and it's a kind of a snotty white liquid, if you leave this, these will form a regular crystal structure, but this bit allows a little bit of movement and gives it the liquid crystal part of its name. If you put these between two sheets of glass, and then this molecule, if you put this liquid between two sheets of glass, and then put a sheet of polarizing material on top and a sheet of polarizing material on the bottom, crossed like this, this is what you get. So here's a little demo I set up. Ooh, try not to drop it. Let's go to the desk camera and put the desk camera actually on the desk, like this. So what I have here is, arrange myself, I have two sheets of glass. Okay, you can just about maybe make out that there's two sheets there. Two sheets of glass, and sandwiched in between is a whole bunch of this stuff, okay? This liquid crystal. And I've attached it to this little charge unit. This has got 3-volt battery inside of two 1.5-volt batteries so that I can apply a charge across the unit. And the way this works, if I've got, here's two pieces of liquid, of polarizing material, okay? And this one, which one shall I talk about? This one here is polarized left to right, and this one here is polarized up and down. So if I just line them up like that, it goes black, okay? Put it right over the thing there. So there's one, there's the other, and it goes black. Oh, it's too much reflection, that doesn't work. If I put my liquid crystal between these cross polars, look what happens. It's see-through. But if I take the material out, the cross polars, ooh, need too many hands, do not let any light through. Put one on each side of here, and it's see-through. If I sort of slide them off gently, like that. So now what you're seeing here is this bit here is just the cross polars, right? So this is the two polarizing filters, no light gets through. But this bit has got my liquid crystal in between and light goes through. And that's because the liquid crystal does exactly what those crystals I showed you under the microscope do. They put a twist on the light, the polarized light, and it allows the light to go through. If I apply a current to this, look what happens. I'll get the angle right. So let me line it up so that I've got line up. Again, so the bottom bit here is just the cross polars, so it's black. The top bit here is just the glass, so it's completely see-through. And this middle bit here is the glass with the liquid crystal, with the cross polars. And when I apply a current, it goes black. And I turn the current off, turn the current on, turn the current off, on, off, on, off, on, off. I've made myself an electrically controlled shutter using a liquid crystal and a little battery, okay? And I can turn it on and off like that. The reason that happens is because, do you remember this? Do you remember I said, don't forget about the nitrogen that's on the top? These things line themselves up between the sheets. And when you turn on the current attracts this end towards, which is negatively charged, towards the positive end, of the positive side of the plates. And as it does that, it destroys the crystal structure. So it goes from being a partially crystal structure to being a completely uncrystalline structure. So you just get a, and it kind of turns over like that. Let me just check on something here. Okay, good, good, good. Sorry, I was just checking on the chat window in there, which some people are posting in. Any questions, remember, press the Q&A button and then you should be able to stick your questions in there somehow. I'm not quite sure. I've never used the Q&A on Zoom before. So anyway, so that's how the individual shutters on your phone are operated using a liquid crystal, a charge, and 2 sheets of polarized material. This does, by the way, explain why when you look at your phone using sunglasses, sometimes it's hard to read the screen and it goes darker. Try rotating the screen as you're looking at it with your sunglasses, because if the polarized filter on top of your phone is at the wrong angle compared to your sunglasses, and mostly sunglasses are just polarizing filters, it will actually block out a lot of the light that comes through from your phone. So which is why sometimes you have to take your sunglasses off to look at your phone and be able to read it. Right, let's see how we do for time. I'm running out of time. I want to talk very briefly about another aspect of the phone screen, because another thing that happens on your phone that makes it into a smartphone is the fact that it's touch sensitive. And the way this works is also down to something that I didn't mention, that nobody picked me up on this. I said that these things, there's a question here, what current is on, does it become uncrystalline or the whole crystal simply turns 90 degrees? Depending on the current, I don't know what current is using, certainly in this system, and this was a polarized sheet, and I pulled off the polarized filters off the top and bottom. I carefully peeled them off. This polarized sheet that I bought and wired up takes a relatively high current, I suspect. There's a good, reasonable amount of current going there. And yes, it does shift all of those molecules through 90 degrees so they're non-crystalline. You can sort of, if you turn it up slowly, you get sort of partial darkening. Excellent. Will that change of shapes and molecules affect objects' mechanical properties? So will it change its mechanical properties? Does that change its mechanical properties as well? Good question. I don't think so. I don't think it changes the viscosity or anything like that. Certainly doesn't change its optical clarity, because this material is fairly see-through. Light does pass through it. Obviously, it causes it to twist, but it goes through. So I don't think it changes its mechanical properties. Right, let's get on to touch sensitivity, and specifically what's known as capacitive touch sensitivity. So I've got here a little box of tricks that I built. I really need more space to demonstrate, but we're just going to have to try on my kitchen table. So what I have here is, inside this box here, there is a BBC micro bit, which is just a tiny little programmable thing. And I was messing around and I decided to try and build a capacitive touch circuit with it. So what I'll do is I'll just calibrate it first. Press that. Oops. Now press this. Now press this. Right, so I've got in here my little capacitive touch circuit, and then I've got 2 conductive sheets of material here. And if I touch the one on the, it's my right, you can see it lights up on this side like that. And if I touch the one on the left, it lights up on that side. And the thing is, I don't even need to actually touch it to get a response. So I'm not touching, I'm just going close. You'll just have to believe me. And you can see the green lights are sort of coming up. Let's try it with this side. It's very sensitive. There's too many things nearby. The red is sort of detecting my presence. Okay, so it's detecting my presence. Now these aren't switches that I'm turning on and off by touching. I'm not kind of clicking a switch or anything. These are capacitive touch detectors. And what they're detecting, what's happening is the microbit is sending current out sort of about once every microsecond to these two sheets of conductive material. And that current goes onto the sheets of conductive material, and then the microbit counts and measures how long it takes for that material, that current, to flow back to it. Right, so it sends the current out, measures how long it takes to flow back. And it does that. And what it's looking for is it's looking for the current to be delayed. And if I touch the sheet here or put my hand near it or on it, what's happening is as that current goes onto the sheet, it actually induces a positive charge. So obviously it's a negative charge that's sent out. A positive charge is induced on the surface of my hand, and that holds the electrons that are now on this plate there for just a fraction of a second. And that's what this is detecting. That is called capacitance. That's what are in capacitors. That's what capacitors do. And that's what it's detecting, okay? And that's how the surface touchscreen of your phone works. It's detecting the capacitance of what it's seeing. Now, the crazy thing about these touch-sensitive material, though, is that this touch-sensitive material, as you can see, I'm holding it and it's lighting up like crazy. If I sort of let go and hold just the wire, okay, it's see-through. And just that should blow your mind. And just pause for a second. What do you know of that is conductive? Metals, carbon. These are all non-see-through objects. Metals are intrinsically non-see-through. The array of electrons in metals means that they are basically not ever going to be see-through. But what you've got coated onto here is a material called indium tin oxide. Now, indium is one of these. We need to do that. And then there we go. Indium, it's highlighted down there. Where is it? No, it's over there. Indium is one of these crazy rare materials, rare elements that is used in mobile phones in abundance. And it's used to coat screens like this. It's indium mixed with tin. So tin, where's SN? Tin is here, right next to it. Indium, tin, and oxygen, and that's coated onto the surface. In this case, these are flexible as well because this is just a plastic sheet. Your phone has indium tin oxide coated glass, and indium tin oxide is it's kind of on the edge of being metallic and being non-metallic, and the non-metallic nature of it allows it to be see-through, but the metallic nature of it allows it to conduct electricity. So you've got this super specific material that is see-through and conductive, and there are very, very few examples of see-through conductive materials. Graphene is an example which hasn't yet been used on mobile phones but could well be, because it is see-through, it's super thin, and it is conductive because it's made of carbon. Right, let's put this over here and let's talk instead. Let's move on to another element. I want to talk about a completely different element. I'm going to talk about neodymium. Now, neodymium, like indium, because of its specific electron structure, gives it some very, very particular properties. And the one that I want to talk about is one that you will find in a lot of material inside your mobile phone. So if I turn that off like that and go to the desk camera. So here's a mobile phone that I picked up cheap. It's been used as replacement parts. The battery would have been there. I don't know what phone it is. LTE smartphone. And actually, when you look at this, you might think it's all electrical components. You've obviously got the screen. That's a very important component, which has got a lot of material in it. But what about the other things? What about the mechanical things in here? And you might not think there's much mechanical inside your phone, but there is. And I'm going to show you a couple of them. What I'm going to do that is put that back in there. Let's go to the microscope. I'll go back to this microscope, turn the light on. So this microscope here is relatively low powered. Let's have a look what we've got here. So we've got a few components here. Let's have a look. This is the camera. That's the camera there. The camera itself is what I like to call it's a mechano-electrical component. But there is another obvious one, which is right down here at the bottom. Inside most mobile phones, you'll find a little device like this, usually in the bottom corner there. If I prise it off slightly, I'm just going to peer down the microscope as I do this. I prise it off like that. Okay, and it's just a little disc. Okay. And now what I'm going to try and do, get that sitting nicely, is I'm going to try and put 3 volts power onto this. So I've got here 2 little prongs attached to a battery. And if I apply some power to this, this is quite tricksy. And that should give you an idea as to what this is. And this is what's known as the vibration alert motor. There it is. Boom. Off it goes. And they're absolutely tiny. And the reason they are able to do that, because they make your whole phone vibrate crazily, don't they? The reason they're able to do that is because of what's inside one of them. So let's open one up. Here's another one I pulled out earlier. There's a little pad of sticky stuff on it that is used to stick it down. And if you open it up, what you see inside looks like that. And it's kind of like a little cute Mickey Mouse smiley face. And if I open that up a bit further, because this bit here comes off, well, it does sometimes. There we go. Oh. The trouble with this is that inside here is that neodymium that I was talking to you about, okay? Because neodymium is used to make this material here. This is a magnet. This is a neodymium rare earth magnet. And neodymium is particularly good at being magnetized and being turned into magnets, and it makes particularly strong magnets. This bit at the bottom is basically, that is just 2 coils of wire, right? Here you've got some contacts, and if I flip this over, that connect to the bottom there, that connect to the coils of wire. You have, so you've now got wire with a current flowing through, which is what sort of comes in at this bit here. The current normally comes in, that's where there should be 2 wires sticking out, but they snapped off, goes through these contacts into this bit here, which then goes into the little round smiley face of little eyeballs, so to speak. Here, just push that in a little bit. And that makes it rotate, because this is a tiny little motor. And that central bit here, this bit here, spins around and around an incredible velocity. And this is an offset weight. So there's a little weight to one side, and that causes the whole thing to vibrate. And that's what causes the vibration inside your phone. I've got time to show you one more. There are several other motors inside your phone. There's one inside the camera. This is what a camera from a phone looks like if you take it apart. This is a little metal bit that comes off. And then inside here is this bit here. Oops. Right. This bit here is the lens system. As you can see, if I flip it over, there's more lenses on the other side. And you'll notice it's got a coil of copper wire around it. And that's because here, on the inside of that little metal shield that I took off, there are more neodymium magnets. And if I kind of hold my forceps near them, it kind of sticks to them, because those little triangular shapes in the corner, those are all neodymium magnets as well. And notably inside there, just out of interest, that beautiful coloured thing in the centre, that is the CMOS center. So the CMOS stands for complementary metal oxide semiconductor. And that's a silicon chip with a whole load of other elements mixed into it that is light sensitive. And that is the thing that produces the image. But you can only get an image out of this because it's got that focusing lens system. And there's a tiny little motor that allows the lenses to focus up and down, just as you would on a big sort of grown-up camera. Okay, I've been talking far too long. Let's do a quick poll. Let's go back to the polls quickly, just whilst we've got time. Let me ask you a few questions for those of you out there listening. First of all, the first question is, do you have to have the latest mobile phone model? Do you really need that new release? Or would you be happy with something older? Or is it just a matter of you'd like it, but you can't afford it? Let's give you a few seconds on that one. Because the thing is, a lot of these elements that are in mobile phones, a lot of these crazy elements, we're running out of them. And they are becoming more and more difficult. Let's close that and get the results on that. They're getting more and more difficult. Yeah, okay, most of you are apparently willing to have an older mobile phone. That's fantastic, great. Next question then. Would you be willing to have a clunky phone, and by that I mean a sort of a slightly chunky phone, if it was made from 100% recycled component with individual components that could be updated? Would that be something? Because let's face it, my new shiny Apple iPhone here, it's super slim and delicious and goes in my back pocket and I can forget about it. But if it was 3 times as thick, I might, be going back to the 80s where I had a big brick. Okay, let's close that and see what people think. What do people think? Okay, we're happy with that. This is fantastic. This is fantastic. Okay, last question for you before I'll come back to the last question, because the reason I mentioned those, oh, he's gone to the question anyway. There you go, that's fine. Are you happy? Are you looking forward to going back to school after lockdown? That is the big question that we're all looking forward to, because whilst these things do allow us to communicate with each other, they're not exactly, let me go to that and go to that. They're not exactly face-to-face communication. Whilst it's fun to talk to people, it would be lovely to be able to have an actual audience in front of you. Let's close that and get the answer to that. How many of you are actually, you're deeply conflicted? Yes, I think actually that's probably where I put myself. I'm deeply conflicted. Right, I'm going to stop there. I'm going to thank Zeiss once again for this fantastic material, and I'm going to thank the Discovery Materials folk for inviting me to come and talk to you. They've got a video they want to tell you about. Now, I've run over, terribly sorry about that, but that's all I'm going to say now. If you've got any questions, stick them in the Q&A and I'll try and answer them for you.
Thank you very much, Martin. That was a fantastic session. I really loved it. You touched upon some very, very important topics, including the problem of recyclability and the sustainability of the technology that we use. So thank you very much once again. I do think we have a few minutes for questions. So I'm trying to look at the chat and the Q&A box. So if you want to ask a question, please use the Q&A box and we'll answer a few questions. So one question is the same phenomenon for all the materials or screens in mobiles like, is the same phenomenon for all the materials or screens in mobiles like this LED? So is it just a new?
I'm not quite sure. I mean, if we're talking about screen technology in particular, the old screen technology used individual LEDs, and that's what OLED technology essentially is. They've gone back to that. The liquid crystal display, fantastically complicated display. They're not very recyclable, to be honest, because the sandwiching of all the different materials is actually very difficult to separate out. You can't really get that glass that's got the indium on it out. I mean, maybe if you crushed up the whole lot and there's plastic mixed into it, and then you've got all this stuff mixed into it, which is hydrocarbons as well. So it's complicated. Another one there, maybe I missed it. Why the liquid crystal is in liquid phase? It's complicated is the answer to that. It forms multiple phases. It's not strictly crystalline. It's not strictly, I mean, it is a liquid. I mean, it's a liquid in all phases because it moves. Even the stuff you get it, I've got some, it's in a little tub and it's just a liquid. And if I take some and put it between two glass sheets of indium tin oxide, I can make it behave like this one that I prepared here, but it doesn't work very well. It's never strictly crystalline. It's never strictly liquid. It's one of those things that they teach you. They sort of say, oh, it's either liquid or it's crystal or it's, and this has crystalline properties, but it's a liquid.
Cool.
What's the difference between capacitive and resistive touch screens? Shall I carry on?
This is the last question. Let's make this the last question.
What is the difference between capacitive and resistive touchscreens? Capacitive touchscreens work the way I described. They're measuring capacitance in different areas. Resistive touchscreens, usually those have a series of wires, vertical wires, and a series of horizontal wires held apart somehow. There's a little bit of, there's a bit of airspace in between or something like that. And when you touch them, you actually make a contact between the two, and that gives you the point. So they're in some ways much more primitive than the capacitive, and the capacitive touch allows you to have multi-touch and stuff like that.
Cool. I think it's time. We're running out of time for this webinar Q&A, so I think we're gonna pause here. Hold on to your questions though, because we're gonna be with you soon. So what we'd like to do now is that we would like to end this webinar. And once we end this webinar, I think Chris is in the background. He can share a link to a YouTube video for you to watch. So Chris, if you use the chat to send the link to all attendees as well, there will be a YouTube video for you to watch while you have a bit of a break, grab yourself a drink, and come back and join us for the next webinar, which is a Q&A with some material scientists and engineers at various stages of their careers. So we have 2 academics, 2 recent graduates, and 2 more experienced graduates that are gonna be there answering your questions about material science and engineering and about careers in material science and engineering. So the questions that you've just posted, so the 3 questions that I haven't answered yet, you know who you are. You're more than welcome to bring up those questions at the next webinar, and we'll be able to answer them.